Hello again, everybody. Welcome back to College Algebra. Today we're in section 2.8 and we're talking about function operations and composition. Now, composition is really important if you're going into calculus or business calculus. You'll need to be able to easily compose functions. So if you're headed in that direction, I hope you'll really pay attention and really develop that skill of composing functions. So some of the things we'll look at in this section are arithmetic operations on functions, that's adding, subtracting, multiplying, and dividing. We'll talk about what's called the difference quotient, and we'll also talk about composition of functions and how to find the domain of a composition of functions. So here we go. First, let's talk about operations on functions. Now, given two functions f and g, we can combine those by addition, subtraction, multiplication, or division. For any x value where f of x and g of x are both defined, then we can get the sum, difference, product, or quotient as follows. F plus g of x is just equal to f of x plus g of x. That is the sum. Remember, plus means sum. So actually this works very nicely. This is about as easy as you could hope for. To find out what f plus g of x is, all you have to do is find out what f of x is, find out what g of x is, and then add them together. And likewise for the subtraction or the difference, f minus g of x is just equal to f of x minus g of x. And likewise for the product, f times g of x is equal to f of x times g of x. Now I will point out here that notice this is a closed dot. The closed dot indicates multiplication. The open dot indicates composition, as we'll find out later. So make sure that when you mean to show multiplication that you're using the regular closed dot. And then finally, f divided by g of x is equal to f of x divided by g of x only as long as g of x is not equal to 0. Because you know that if g of x were equal to 0, we'd have f of x over 0, and that would be undefined. So any x values that cause g of x to equal 0 will have to be left out of the domain. So if we add, subtract, multiply, or divide two functions and we get a new function, what will be the domain of that new function? That's what we need to look at now. So for functions f and g, the domains of f plus g, f minus g, and f times g are all the same, and basically that domain will include all real numbers that are in the intersection of the domains of f and g individually. So you figure out what the domain of f is, you figure out what the domain of g is, and where the two overlap, that will be the domain of your new function, as long as you're either adding, subtracting, or multiplying. However, as you probably noticed on the last slide, we have to be a little careful when we talk about the domain of f divided by g. It's almost the same, but we have to be careful. The domain of f divided by g includes those real numbers in the intersection of the domains of f and g, for which g of x is not equal to 0. So it's the intersection of the domains of f and g, just like the sum, difference, and product, but in addition to that, we have to leave out any x values that cause g to equal 0, because remember, g is in the denominator of this quotient. Now, sometimes when students see the notation g of x cannot equal 0, they think that it means that literally there's nothing you can plug into g that would make it come out 0, but that's not what they're saying. They're saying that if there is an x value that can be plugged into g so that g of x equals 0, then that x value has to be left out of the domain of f divided by g, because that would cause f divided by g to have 0 in the denominator, and we cannot allow that. So here is example 1, and this says let f of x equal x squared plus 1, and let g of x equal 3x plus 5, and find each of the following. So for part A, they're asking us to find f plus g of 1. Now, using the definition that we got a couple of slides back, we know that f plus g of 1 is just going to be equal to f of 1 plus g of 1. So we just need to find these two individual values and then add them together. Plugging 1 into the f function, f of 1 is going to be 1 squared plus 1. That's 1 plus 1, which is 2. Plugging 1 into the g function, that's going to be 3 times 1 plus 5. That's going to be 3 plus 5, which is 8. And now f of 1 plus g of 1 is 2 plus 8, which is 10. So f plus g of 1 is 10. Now let's look at part B. So here we have f minus g of negative 3. Well, using the definition that we got a couple of slides back, we can say that f minus g of negative 3 is equal to f of negative 3 minus g of negative 3. Okay, so we just need to figure out what each of these values is and then subtract them. Plugging negative 3 into the f function, f of negative 3 will be negative 3 squared plus 1. That's going to be 9 plus 1. That's 10. And g of negative 3 is going to be 3 times negative 3 plus 5. That's negative 9 plus 5. That's negative 4. So now f of negative 3 minus g of negative 3 is 10 minus negative 4, which is equal to 10 plus 4, which is equal to 14. So f minus g of negative 3 is equal to 14. And continuing with example 1, we have part C. This says f times g of 5. So we know from our definition of function multiplication that f times g of 5 is just equal to f of 5 times g of 5. Now f of 5 will be 5 squared plus 1, and that's 25 plus 1, which is 26. G of 5 will be 3 times 5 plus 5, and that's 15 plus 5, which is 20. And now f of 5 times g of 5 is 26 times 20, which is 520. Now for part D, f divided by g of 0 is equal to f of 0 over g of 0, provided, of course, that g of 0 is not equal to 0. Because if g of 0 were to equal 0, then we would have whatever the top number is divided by 0, and that would be undefined. So this will only have meaning as long as g of 0 is not equal to 0 itself. So now let's evaluate each of these. Plugging 0 into the f function, 0 squared plus 1 is 0 plus 1, that's 1. And plugging 0 into the g function, g of 0 would be 3 times 0 plus 5, which is 5. And then to put it together, f divided by g of 0 would be f of 0 over g of 0, which is 1 over 5. And since this can't be simplified, that's our final answer. And now let's look at example 2. And in this example, they'll be asking us to evaluate this function operation at x. So in other words, we won't have a number to plug in here. So all we can do is go by the function operation definitions that we got earlier in the section and do any simplifying steps that are available to us, and when we've done all we can do, we'll just stop. So here we have f plus g of x, and we can restate that as f of x plus g of x. We know that from the definition. Now f of x is just equal to 8x minus 9, and g of x is just equal to square root of 2x minus 1. Now if there were any terms here to combine, then we would do that. But in this case, we have an x term and a constant, and then we have a radical. So none of these can be combined, and this is our final result. Notice that the instructions say to give the domain of each function. Well, if you just look at our function that we came up with here, you can tell that as far as this term is concerned, x could be anything from negative infinity to positive infinity. In other words, you could plug in any number you want here. However, this x is under the radical, and remember that we can't allow x to be anything that would cause this radicand to be less than 0. So we'll need to find the x value that causes this radicand to be 0 and make sure that x stays that much or more. So let's write an inequality, and let's say that 2x minus 1 needs to be greater than or equal to 0. And remember, we just have to keep this 0 or more. So if that's true, that means that 2x has to be greater than or equal to 1, and that means that x has to be greater than or equal to 1/2. So in other words, the domain of this function is any x value that's 1/2 or more. In interval notation, we would say that the domain is bracket 1/2, comma, infinity, parentheses. Now let's look at part B. And according to our definition of function subtraction, f minus g of x is going to be equal to f of x minus g of x. So let's just take our f function, which is 8x minus 9, and subtract from that our g function, which is square root of 2x minus 1. Now again, if there were any terms to combine here or any operations that we could complete, we would do that, but there's not. So this one is finished. And now let's talk about the domain. So again, you see the same thing here that you saw on the sum. We know that we just can't let x be anything that would cause this radicand to be less than 0, and therefore we could go back through this again, but it's going to give us the same domain. The domain of f minus g of x also needs to be bracket 1/2, comma, infinity. And now on part C, of course, we're looking at the product of f times g of x. We know, according to our definition, that f times g of x is going to be equal to f of x times g of x. So we just need to take our f function and multiply it by our g function. Now again, this is all the multiplication we can do, because with this g function being under the radical, we can't carry out FOIL or anything here. All we can do is leave it as 8x minus 9 times square root of 2x minus 1. And notice that the domain of this product would be the same as the domain we found for f plus g and f minus g. Because if you're just looking at this term, x can be anything, but if you look at what's under the radical, we have to make sure that 2x minus 1 does not become negative. So the domain of this function will need to be the same as the domain of the previous two functions for the same reason. So I'm just going to say that the domain of f times g is bracket 1/2, comma, infinity. And now for part D, we have f divided by g of x. Okay, by definition, that's f of x divided by g of x, as long as g of x is not equal to 0. So any x values that cause g of x to be 0 will have to be left out of the domain of this function. So let's go ahead and plug in our functions. F of x in the numerator is 8x minus 9, and in the denominator we have g of x, which is square root of 2x minus 1. Now I'm sure you remember from the previous three parts that x needs to be 1/2 or greater in order to keep this radicand 0 or greater. But now that this radical is in the denominator, we can't even let this radicand equal 0, because we can't let the denominator equal 0. So it used to be that the domain had to be bracket 1/2, comma, infinity, but now we must also leave 1/2 out of the domain, because that would cause the entire quotient to become undefined. And so now the domain of this function is not bracket 1/2, comma, infinity, but it's parentheses 1/2, comma, infinity. Now here in example 3, we're going to practice doing these function operations 3 different ways. First, we're going to look at it where we have two functions on a graph. Then we're going to look at it in table form, and then we're going to look at it again in expression form. So let's just take each of these one at a time. Here we have f plus g of 4. Now you know that that means f of 4 plus g of 4. So the f function is the one you see here in blue, and the g function is the one you see here in red. Remember, these function values are just the y values at the stated x value. So f of 4 means find the y value for the f function when x equals 4. And the same thing for the g function. So f of 4 means we go out to where x equals 4 and see what the f function's y value is. And when x equals 4, the f function equals 9. But when x equals 4, the g function only equals 2. So f of 4 plus g of 4 is 9 plus 2, which is 11. Now let's look at f minus g of negative 2. So that's going to be equivalent to f of negative 2 minus g of negative 2. Now when x is negative 2, the f function is actually negative 3. But when x is negative 2, the g function doesn't even exist. So to do this subtraction, we'd be doing -3 minus an undefined number, and of course we can't do that, so that value itself is undefined. Now for the next part, we have f times g of 1. So of course this needs to be restated as f of 1 times g of 1. So that means we need to go to where x equals 1 and find each of these function values. When x equals 1, the f function equals 3. And when x equals 1, the g function equals 1. So f of 1 times g of 1 is going to be 3 times 1, which is 3. And now let's look at f divided by g of 0. Of course, that's f of 0 divided by g of 0. When x equals 0, the f function is 1. But when x equals 0, the g function is 0. So what we have here is 1 divided by 0, which is undefined. So even though neither one of these individual functions was undefined at 0, the quotient itself is undefined at 0. Now, still on example 3, we're going to go back through the same 4 questions, but this time instead of looking at the graph, we're going to be looking at a table. So let's start with f plus g of 4. So that's going to be f of 4 plus g of 4. Now when we go to the table, we have when x equals 4, the f function is 9, and the g function is 2. So 9 plus 2, of course, is 11. On the second part, we have f minus g of -2. So that needs to be restated as f of -2 minus g of -2. So when we look at the table, when x is -2, the f function is -3, but the g function is undefined. So -3 minus something undefined is also undefined. On the next part, we have f times g of 1. So of course that's f of 1 times g of 1. So when x equals 1, the f function equals 3, and the g function equals 1. So f of 1 times g of 1 is 3 times 1, which is 3. And for f divided by g of 0, we have f of 0 over g of 0. When x equals 0, the f function equals 1, and the g function equals 0. So f of 0 divided by g of 0 is 1 divided by 0, which is undefined. And now finally we're going to look at the same 2 functions, but this time using the expressions instead of the graph or the table. So we'll have f plus g of 4, and that's of course f of 4 plus g of 4. Now we'll plug 4 into each of these functions. F of 4 is 2 times 4 plus 1. That's 8 plus 1, that's 9. G of 4 is square root of 4, that's 2. So f of 4 plus g of 4 is 9 plus 2, which is 11. On the second part, f minus g of -2 is f of -2 minus g of -2. So we'll find each of these by plugging -2 into each function. F of -2 is going to be 2 times -2 plus 1. That's -4 plus 1, that's -3. G of -2 is going to be square root of -2. Now that would be an imaginary number, but as far as our function is concerned, it's undefined. So g of -2 is undefined, and we'll have to say that f of -2 minus g of -2 is -3 minus an undefined number, and the result is undefined. For the third part, we have f times g of 1. So of course this is f of 1 times g of 1, and we'll need to evaluate each of these. So we'll plug 1 into the f function. F of 1 is 2 times 1 plus 1, that's 2 plus 1, that's 3. And g of 1 is square root of 1, and the square root of 1 is 1. So now f of 1 times g of 1 is 3 times 1, which is 3. On the last part, we have f divided by g of 0. So of course we restate that as f of 0 divided by g of 0, and we'll need to plug 0 into each of these. So f of 0 would be 2 times 0 plus 1, that's 1. G of 0 would be square root of 0, that's 0. So now f of 0 divided by g of 0 would be 1 divided by 0, which is undefined. Now we'll finish this section up in part 2.